All right, hi everyone. Today we're going to work with logs and exponents. How do we use logs? We know how to use exponents. Exponents are pretty easy. It's like multiplication. But then when we learned division, it took us a mess with our brains, and we had to relearn how to do that. But let's go get started here. So we're going to do exponents first, real quick. Some real quick rules for exponents, such as 3 to what exponent is 9, right? That's an easy idea. 3 times 3, how many times is that 9? So we're saying this happens twice. So we write that as an exponent as 3 squared is 9, right? If I say 3 to what exponent is 81? Well, an exponent is we're multiplying something over and over and over. And since the x is in this exponent position, that means we don't know what it is, but we can figure it out. 3 times 3, that's 9. Okay, we're not there yet. Give it another 3. We're now at 27. All right, we're not there yet. Give it another 3. We are now at 81. All right, hey, so 3 to the 4th power is 81. So for the most of our lives, we could probably figure out if it's a nice whole number. In Algebra 2, we also learned about fraction versions of this, nightmare fractions. Oh yeah, let's look at fractions. If I say 3 to the 1/2, that's not a whole number. Okay, but this turned out to be another way of writing the square root of 3. Why would that be true? Well, let me give you an example. What if I had 2 3's here? 3 squared, the square root of 3 squared is, because we have 2 3's, that's just 3. But let me show you this in exponent form. If I wrote this as, instead, the square root of 3 squared is 3 squared to the 1/2 power, right? How do we know this? Because 1/2 exponent is really a square root. Right, let that squeeze into your brains. Right, a square root here is really a 1/2 exponent. So I wrote the square root as a 1/2 exponent. If we multiply this together, 2 over 2 is just 1. That's equal to 3. Back to our answer over here. So we could write fractional exponents, but they turn out to be radicals instead. If I wrote, let's say, 27 to the 1/3 power, this is not a square root this time. I'm looking for sets of 3, a cube root of 27. Let's see if we break up 27. I feel like we can break up 27, right? 27 is a number that we oftentimes see. It's 3 times 9, which is 3 times 3. All right, we have 3 27s. So this, of course, is just 3. But let's write this a different way. Let's actually go back over here. 27 we said was 3 cubed to the 1/3 power. Are you guys okay with me replacing 27 with 3 cubed? If I multiply them together, it's 3 over 3. And yes, we still get the same answer looking at it in an exponent way. There's also one more way that we looked at exponents besides fractions, and fractions was probably the hardest way for us to look at it in Algebra 2, is what if we had negative exponents? And if I wrote 3 to the -1 power, in Algebra 1 and Algebra 2, we learned that this is another way of writing a fraction of 1 over 3. Okay, 1 over 3. And this was a notational way for us to say how many 3's do we have? Well, we have 1 3, but it's negative, so it's on the other side. Now, let me show you where this is, one way this is derived, okay? Is if I give you 3 squared divided by 3 cubed. A very classic Algebra 1, Algebra 2 way of doing this is just writing out the numbers. As you can see, the 3's divide out to become 1, but we're still left with a 3 on the bottom, so we're left with 1 over 3. Great, and that's our answer. An Algebra 1 way of looking at this, and Algebra 2 way, is what if I rewrote this as, our rule was, if I'm dividing powers, I am subtracting exponents. So we end up saying 2 minus 3. Or we could have actually written it this way first. If I give myself a negative exponent, this is 3 to the 2 power times 3 to the -3 power. If I'm multiplying powers, I am adding exponents. Hopefully you remember that. And if I'm adding them, this is a plus a negative. And with 3 to the -1. And we're back to 1/3 on the bottom. So to express exponents, there's a lot of different ways for us to handle that. And it's really kind of, if I do it one way or do it another, it's really just a preference issue rather than you must do it this way. Now, if I give you a bigger number, if I say 3 to the 24 divided by, or 21 divided by 3 to the 24, well, how many 3's do we have left over? Well, if I rewrite it as 3 to the 21 times 3 to the negative 24, right? Because negative means you're from the bottom, or not from around here and on the wrong side. This is 3 to the 21 minus 24 is 3 to the negative 3, which is 1 over 3 cubed. But of course, if we did it our algebra way and we wrote 3 a bunch of times, 3 a bunch of times, we would be left with 1, 2, 3 left over, giving us, everything else would have canceled out, leaving us a 1 over 3 to the third power. And we don't want to do that. That takes too much time. So that's one of our ideas. We also have another rule about exponents, and I think this is one of our last ones, is that if I say 3 to the 0 power, well, how many 3's do we have? We have none. So we have a default answer to this, and this is always true. 3 to the 0 power is always equal to, hopefully you might remember it, uno, right? Always equal to 1. Now, why is it equal to 1? I used to tell kids, like, hey, if I say x squared, y cubed, and z0, do you have any z's? I don't have any z's, but this doesn't mean 0. This just means we don't have any z's. Okay? Just because we don't have a number, that doesn't mean it's a 0. But I thought about a different way of talking about it. What if I write 3 divided by 3? Isn't this 3 to the 1 power times 3 to the negative 1 power? And if I go ahead and add those exponents up, we end up with 3 to the 0 power, which is equal to 1, like we first started. 3 divided by 3 is 1. Same thing if I divided them using exponents. 3 to the 1 power times 3 to the negative 1 power, they would cancel out to become 0. 3 to the 0 power is the same as me just saying 1. Okay, so a couple of things we want to make sure we are kind of cool with here. Okay. Now, so far we've been dealing with nice whole numbers. Nice whole numbers. But well, let me give you a question where there might not be an answer. 3 to the x power is equal to 10. Now, is there an answer here? Well, let's do a little guess. If I say 3 to the 1 power, that's 3. 3 squared, that would be 9. 3 cubed, 3 times 3 is 9. 9 times 3 is 27. So isn't 10 someplace between? X is between 2 and 3, right? That's my exponent. X is someplace stuck between 2 and 3. And that would give you 10. Now, numbers between 2 and 3 are not whole numbers, are they? They're decimals. And math people had to come up with a way to answer this question, because you know what? In real life, most numbers are decimals. When you go to Ralph's, when you go to 7-Eleven and you give them $1 to buy something, nothing costs exactly $1. Everything will either, I mean, you're going to get change someplace, right? And you usually leave those pennies in the drop a penny off here box. Okay? So what we want to notice is that it's okay to have a decimal. Now, we have a special tool now to talk about how do we solve for exponents. And that's going to be logs here. Logs solve for exponents. And that's a tool that we're going to focus on today, is how do we use logs to solve for exponents? Because 3 to the x, a radical is not going to work here. I can't say 3 is equal to, or the radical of some variable. That tool doesn't work. That does not really exist. What exists though is us using a log tool. Now let's go ahead and talk about logs. So this is not good, right? Okay, so let's go talk about logs. So our first thing is to say how to use logs. Okay, well, here is a basic use of a log. If I say log base 3 of 9, the answer is 2. Why did I say the answer is 2? Because remember what I just said here? Log solve for exponents. The answer here is an exponent. Exponent of what? Here's the base, and here's my answer, the result of that. So I call this song the circle of logs. 3 squared is 9. The circle of logs. I'm going to get copyright strike because I said the circle of logs. And this circle of logs, please let it zone into your brain, is how we read logs. Log 10 of 100 is equal to 2. Why? Circle of logs, 10 squared is 100. Log solve for exponents. 10 to what exponent would equal to 100, right? Well, the answer is circle of logs 2. 3 to what exponent would equal to 9? Circle of logs 3 to the second power would give you 9. Let's keep going. Log base 5 of 125. What exponent would give you 125 if I just kept multiplying a bunch of 5s together? Circle of logs 5 to what exponent would give you 125? That would be 3. Right? 5 times 5 is 25 times 5. That's 125, right? 5 cubed. That's the exponent that will give me 125. Circle of logs. Okay, log base, let's do 25, okay? Of 5. What exponent, this was a tricky one. What exponent of 25 would bring me back down to 5? This is a tough one. And let's see, how can I get 25 to become 5? 25 to what exponent would give you 5? Maybe you got it, maybe you don't. Maybe you're thinking the square root of 25. Isn't the square root of 25 5? So this is actually 25 to the 1/2 power. And that's actually our answer here. Circle of logs, so this is going to be 1/2 or 0.5. Because 25 to the 1/2 power can be rewritten because a fractional exponent is really a radical. Radical 25 is equal to 5. And that's a true statement. Now, these aren't always easy. And that's why logs are helpful. Now, if you guys have a calculator with you, I want you guys to take it out. And we're going to see how can we type this out on a calculator. Because the calculator actually only gives you, depending on the type of calculator that you might have a nice fancy calculator that it has what we call pretty font, pretty type, and you can write it as we see it. And if you don't, I'm going to have to teach you guys a couple of rules of logs to get there. Now, take a look at your calculator. Let's go take a look at my calculator here and see what that looks like. And let's see, this is my calculator here. And you'll see, you do see a log here. But if you see the log that they have here, it has a little 10 there. Because this is automatically log base 10. Log base 10. Some of your calculators will actually have a button that looks like log, empty box, empty box. Now, if you have this calculator, you have a nice fancy calculator, a modern calculator made within the last probably 8 years. And this, you can literally plug what we just plugged in here. You could have wrote log, little box, write 25, big box, write 5, and hit enter, and see that the answer will give you 0.5. And if you have that calculator, you're already winning. But if you don't have that calculator, we're going to need a special identity right now. So logs themselves are a new system of writing numbers. And with every system of writing numbers, we have to learn how to do the most basic of operations. How can I add logs? How can I multiply logs? How can I take the exponent of logs, right? Everything we would do with simple numbers. And we're going to come up with those rules later, but today we're just going to work on the conversion of how to change one log to another. So let's go ahead and work on that conversion, and then we'll come back and I'll show you guys how to use that on your calculator. So first, let's go ahead and do conversion. Converting into a log from an exponent. Okay, we're going to work on converting into a log from an exponent. So let's go and talk about what am I talking about. What am I saying here? If I say 5 squared, we know this is 25, yes? Okay, 5 squared is 25. So how do I write this in its log form? So here's our exponent form, and here, over here is going to be a log form. And this is how I teach it. We write the first word log. What is the base that we're multiplying here? What number are we repeating multiply, multiply, multiply over again? Hopefully you notice that's going to be the 5 here. Let me maybe color code this a little bit for you guys. Let's make this red. See, that's going to be red. That's going to be red here. And that's where we write the 5, base 5. Remember we said circle of logs, circle of logs. 5 to what exponent are we looking at? 5 to the second power. Let me go ahead and change this to yellow. The yellow part always goes on the other side. That's going to be a squared. Oh, sorry. That's going to be a squared. Remember, log solve for a circle of logs. 5 to the second power is 25. That's right, 25 here. And hopefully you're not colorblind like I am. And you can see that all these numbers are actually rewritten in the log version, just in a different place. Okay, just in a different place. Because logs don't solve for your exponent value, it solves what is your exponent. Okay, it doesn't solve for what's the answer. 5 squared is 25. It doesn't give me 25. It says what answer, what exponent would have given me, counting by 5s, to get me to 25. So we can rewrite this a couple times. Let's try another one. If I say 7 squared is 49. How do I write this in log form? Once you guys go ahead and try to write this in log form, you need to write something on the bottom, something in the answer, and something in these 3 positions. If you guys could fill that out for me. 10 to the cube power is 1000. Please go ahead and write this in log form. Let's do one more. So you're rewriting this in the log version of it. Okay? You're rewriting this in the log version of it. Okay, let's go ahead and get started. What's the base in this problem? The base is 7. 7. The answer is 49. And the exponent is 2. So these are the positions we have to rewrite everything if you're going to write something in the log version. The base is 7. The answer is 49. And what exponent got me to 49? 7 squared. Circle of logs. 7 squared is 49. Look at our next problem. Base is 10. Exponent is 3. Answer is 1000, right? So 10 to what exponent? 10 to the third power is 1000. Circle of logs. Next one, our base is 2. Our answer is 32. What exponent gives us 32? 2 times 2 times 2 times 2 times 2. That's 4, 8, 16, 32. Yep, that's 5. I needed 5 2s to get me there. So this idea of logs, they help me find out what the exponent is. Now, I'm going to have you guys try this on your calculator. Whether you have a nice calculator or not, I'm going to teach you guys this new rule, and this is for this is what I call it. I call it my calculator log. But the rule is if I divide logs, log base 3 of, actually no, that's the log, that's right this way. Log of 10, that's not 10, that's the log of 5 divided by log of 3. This can be rewritten, and this is what we call change of base. This is what it's actually called, change of base. Change of base. This becomes log base 3 of 5. Now 3 to what power gives you 5? That is not a whole number. 3 times 3, so 3 times 2 is 9, and 3 times 1 is 3. And the answer 5 is between 3 and 9. So it's 1 point something, 1 point something. And I want you guys right now to see if you guys can figure it out by typing log 5 divided by log 3. Now, if you have a cheap scientific calculator, a $5, $10 one, you're going to type it this way. You're going to type 5 log divided by 3 log. That's how you're going to type on your calculator. 5 log divided by 3 log. And then hit the equal sign at the end. Now I'll demonstrate that on my calculator here. But I don't have logs. Let's find logs. There's my log. Oh, hey, hi. We're going to 5. Let me clear it first. 5 log divided by 3 log equals 1.46. I'm going to round it 1.465, rounding up. Okay, I rounded up here. So this is an overestimation. Now if you look at your calculator, near that log you should also have an exponent button. And in this case I don't have exponent. I have this xy right here. You guys see the xy? I'm going to try it. If I write 5 to the, no, not 5, I'm sorry, 3 to the 1.465 exponent, would that give me 5? Circle of logs 3 xy, oops, let me clear it. 3 xy 1.465, we get approximately 5, don't we? Now this is how we're going to solve for those unknown exponents. Not every exponent is going to be a whole number. Sometimes it's going to be a fraction, sometimes it's going to be a decimal. That's fine, but we now have a calculate operation to find that. So let's go ahead and see how we would put this example into use. Right? So it is true that 3 to the 1.465 would give me the 5. Alright, let's look at another problem. If I ask you 7 to what exponent is equal to 10? Okay. Can 7 to some exponent become 10? Sure, but it's not going to be a nice easy number. So let's rewrite this as the circle of logs. Write the word log. Why am I using logs? Because logs solve for exponents. Log solve for exponents. Great, thank you. Log solve for exponents. Actually, no, I should use the Apple calculator. Log solve for exponents. So let's convert our exponents into our log form, please. What do I write here? Here. And I'll say this is equal to x, right? Okay, the base is 7. This is the base here. So we're going to write that O is on the bottom. The answer, 7 to what exponent is 10? I don't know what that is. So the way we write this problem in a calculator, we write log of 10 divided by log of 7. And this is what we call change of base. Because the calculator, if you remember from Algebra 2, only contains base E and base 10. It doesn't have any other bases. So I want you guys to practice you writing log base 7 of 10 as log 10 divided by log 7. And let's see what answer you end up with. I'm going to go ahead and show that on my calculator over here. Let's see if you guys can get the same answer I did. You write 10 log, because it's going to log whatever, it's going to do the operation on whatever number it sees. If I write 10 I want it to log that number that I see. Log it. Okay, that becomes a 1. Great. Divided by 7 log. That's what you guys are typing in your calculator. And then hit the equal at the end. Divided by 7 log equals. And my answer is 1.183. Yep. 1.183. So this answer up here would have been 1.183. That means, darn it, 1.183. 83. And that means when I go backwards, our exponent way back to the top, 7 to the 1.183 would give us approximately 10. Hey, that's it. That's the lesson for today.